Hey, I'm Charlie.
I'm John, and this is our extra credit video project for Professor Kishimoto. Today, we're talking about the applications of electricity and magnetism in a sound system.
So we're going to be talking about two major topics we learned in class this semester.
During the beginning of the semester, we learned about electrical wiring and electrical power. So now we're going to go in depth in the hardware components of the sound system developed by Charlie. Next, what we learned later in the semester is wave interference, and this involves how the sound waves projected from the system interact with each other and interact with their surroundings.
We'll be giving an experiment of the wave interference and giving you a tour of the sound system in order to see the hardware components.
Good. Hey, so this is the sound system I built when I was in high school. We use it in the stadium for ultimate frisbee. Altogether, it can be used at 4,000 watts, but we're running on 8 ohms per channel, so it's only running at 2,000 watts currently. So the way it works is that these are two amplifiers. The first one is for the mid and high range speakers on the front, and the bottom one is for the subwoofers on the bottom. So I'm going to go ahead and show you what's going on here. On the top, we have 4 6x9s, which are good for the mid and high, which you find in cars. And then on the bottom here, you have 2 8-inch subwoofers. And they're separate, but they are wired together through their inputs. So how this works in here, there are the 4 speakers coming in top that are wired together. There's an aluminum slab that separates the box into 2 cavities so that the waves don't interact with each other. This is a little complex, what's going on the inside of the box, so we're not going to talk about this in this project, but this isolates the two in order to have better sound quality.
Let's break down the hardware components a little bit more. In Charlie's sound system, there are 2 separate circuits, both of which are wired in series. Because of this, they create an impedance of 8 ohms each. Now, the first circuit is connected to the mid-range and upper-level speakers, while the second circuit is connected to the lower-range subwoofers. Here, we can see the wiring Charlie had designed. We can clearly see these speakers labeled as 4 ohms and 1200 watts. But due to the wiring, which we can see here, the impedance was changed to become 8 ohms. This was due to the fact they did not need the extra power of 1200 watts. By doubling the 4 ohm impedance, we can create a 600 watt output. This is because these speakers were powerful enough to overpower the bass provided by the amplifier. And because of that, that extra power was not necessary or needed. And so a power reduction was necessary.
So in the box right now, the amplifiers run off of 110, which is AC that comes out of the wall. But when I want to use the sound system in my car, we don't have alternating current, we have direct current. So in order to accomplish this, so I can use the sound system in the car, we hook it up to a battery. In order to hook AC up to DC, you need an inverter, which changes DC into AC, which these amplifiers run off of. I solved the battery problem by using 2 6-volt batteries from a golf cart and connecting them together in order to create one 12-volt battery.
Alright, let's break down wave interference. Represented by these 2 circles are our speakers. So we can see from the central point of one speaker to the other, we have a difference of 12 inches. This is going to create constructive hotspots as well as destructive dead zones. Our speaker system right here is made so sound waves will be emitted at 400 hertz. This means both of our speakers will be in phase with each other, and we'll be able to calculate our hotspots and dead zones along a perpendicular line. We'll collect data points perpendicular to the speaker using Audacity, a mobile program to collect sound data, on a movable chair, as we will slide it across and hear what the speaker is emitting.
Okay, so here's our experiment. So we're going to be using the speaker, tracking it with the laptop. In order to make this a little simpler, I'm going to go ahead and turn off the subwoofers just so there's not more interference than necessary. So what we have is a signal generator. I'm going to be playing the speaker at 400 hertz and moving this laptop along, and getting the different readings out, which we will record and put a copy of. Hopefully it comes out okay. So, just to start, it's going to be higher volume than it seems. We're going to have a high volume, so we take out the noise of the chair moving. So we're playing at 400 hertz. You can see this bar right here is every time my voice makes a sound, it goes up. So we're gonna be as quiet as possible and here, but this bar should fluctuate as we move the chair. All right, so this is the video of the sound. As you can see, like the fluctuations, the peaks are us making noise, but like, as you can see, there's like that's a hot spot, and like that's a dead zone. Like hotspot, dead zone, hotspot, and dead zone. And then you can kind of see more and more. So, based on that, we showed how, even though they're not extreme, there's still high points and low points along a perpendicular line. Hey, thanks for watching our extra credit video.
We had a lot of fun making it, and we hope you learned a little bit watching it.
We got to tell you, Professor,
This semester rocked.
Have a great summer.
See you guys later.
Have a good night.